So we have a F is a finite family of
Speaker of the mic.
F is a finite family of convex sets in Rd. And now instead of every two intervals intersecting, we have the following condition. If for every subfamily G in F of size at most D plus 1, the intersection of G is non-empty, which I'll denote by this. Then the intersection of the whole family is non-empty. And apart from the fact that in D equals 1, we retrieve back this statement, one might wonder why we chose D plus 1 here. And it turns out that, so the constant D plus 1 is sharp in the sense that we can't have any constant less than D plus 1 here for the following reason. We take the simplex. In Rd, it has D plus 1 facets. And any D facets intersect at a vertex. So in R3, any 3 facets intersect at a vertex, which satisfies this condition. However, the intersection of all the facets is empty. So D plus 1 is very necessary here. And so my talk is about quantitative versions of Helly's theorem. So to motivate quantitative versions, I'm going to write kind of a pseudo statement. This isn't a real statement yet to motivate where we're going. So a quantitative version of this statement. Again, we let F be a finite family. Yes, of convex sets in Rd. And if the intersection of any K sets in F, where I'll define what K is later. It might not be D plus 1 in this case. So if the intersection of any K sets in F is large in some quantitative sense, and I'll also define what that is, then the intersection of all the sets is not too small. In some sense that doesn't depend on F, hopefully. But before I define these words large and not too small, I wanted to say a word about what K is. K must be, K cannot be less than 2D. Because of the following example. If we take a cube, so a square in the plane, and we consider it as an intersection of 4 half spaces, kind of each pointing inwards, they're closed half spaces. Then note that any 3 of them have unbounded intersection, 2D minus 1, which, but the intersection of all K of them is this cube, or this square, which can be made arbitrarily small. So if we kind of bring these half spaces close to each other. So with K equals even 2D minus 1, and a cube in D dimensions has 2D facets, this would not make sense, this sort of image. Okay, so our notions of size are going to be volume of a convex set, or a convex body, convex compact set. This is standard D-dimensional Lebesgue measure, and diameter, okay, which is the maximum distance between 2 points. And if we let K equal 2D, if we consider the intersection of any 2D sets to be large, then the statement actually holds, a version of it holds. And this is our starting point. So there's a theorem by Baran Tchaikovsky and Koch from 1982. That is the following. There exists a constant C only depending on the dimension. And it's positive, such that the following statement holds, such that for any finite family, F of convex sets in RD, if for every subfamily G and F of size at most 2D, we have that the intersection is non-empty. Then, oh, not the intersection, sorry. That the volume of the intersection is greater than or equal to 1. So any 2D sets, we take their intersection, they have kind of a large volume, then the volume of the full intersection is greater than or equal to a constant, as this constant C. Any questions about this statement? So they also proved in 1982 the same thing, except we replace every instance of volume with diameter. So in this case, we have an F as there exists another constant C prime, such that for any finite family F of convex sets in RD, if we look at every subfamily of size 2D and their diameter of intersection is at least 1, then the diameter of the full intersection is another constant C prime greater than 0. So this this motivates kind of. So I said before actually that we're interested in kind of looking at the contrapositive kind of an existence of a certain subfamily, seeing the contrapositive of the statement. So I'll restate this theorem as follows. So again, there exists constants C1 greater than 0 and C2 greater than 0, such that for any finite family F of convex sets in RD, if the condition is for all subfamilies G and F of size, we have a finite family F of convex sets in RD, then there exists a subfamily G this time, such that the volume of the intersection is at most C1 times the volume of the intersection of F, or the same statement for diameter. C2 and the diameter of the intersection. So what I did is I took their theorem and I took its contrapositive. And I also kind of didn't fix any volume type. I just sometimes this theorem is stated where the volume is of the full intersection is 1, but running it like that. Okay, so with these two statements, I want to introduce this definition of a parameter. We'll keep track of how small can we make this constant C1 such that this always holds for every finite family F of convex sets. So here's the definition. Let me label these equations star and double star. Let d of d be the minimal C1 such that star holds. And there exists such a C1 because of the theorem by Brian-Kachelski. And the same thing, let delta of d be the minimal C2, such that the diameter statement holds. People have been thinking about this problem since the 80s, and I want to tell a little bit of the history behind this problem. And then we'll move on to the main results, and we'll talk about some proof ideas, and finally we'll talk about further directions.
Let me just stop you for a second. Feel free to stop if you have any questions, comments, you want to yell, you want to throw something at the speaker, whatever.
Please throw tomatoes, yeah. Okay, so some problem history. So Baran, Kachelski, and Pak showed more than just the existence of these constants v of d and delta of d, but they have an explicit bound. V to 2. And they showed that v of d is at most d to the 2d squared. And they also showed that delta of d is d to the, at most, d to the 2d. They conjectured that.
Sorry, what is this? Less than or equal to d to the
Yeah,
2d, okay.
2d squared. And
I
this,
see the 2d squared, got it.
yeah, and this one's 2d. And they conjectured that this is kind of much weaker than what the actual truth is. They conjectured that there exist positive constants such that v of d is approximately d to the C1d, and that delta of d is approximately C2 times the square root of d. So for the bottom one, it kind of comes from this being kind of proportional to the main diagonal of the cube. And the first big breakthrough was by Marton Naxodi in 2015, who showed that the volume conjecture holds for, showed the v of d is at most dv to the 2d. And C the positive constant. These constants are always going to be positive. Brazidikos in 2017 improved the volume bound to CD to the 3D over 2. Yeah. In 2018, Brazidikos found a polynomial bound for the diameter. So instead of d to the 2d, he found it's at most CD to the 11 over 2. And finally, Ivanov and Nasodi, most recently in 2021, showed that delta of D is at most 2D cubed. And there are also lower bounds that they showed that were proven. So for the volume bound, Nasodi showed in 2015 that in fact, linear factor in the exponent is true. So he showed that phi of D must be at least CD to the D over 2 in 2015. And in this paper in 2021, Ivanov and Nasodi showed that the diameter is at least CD to the 1/2. Any questions so far? And one other result that I found to be kind of particularly relevant is this result by Dylan and Soberon in 2021. And they showed that you could actually get delta of D is C squared of D, but you need to sacrifice something. So you have let F be a finite family of convex sets in RD. If for all subfamilies G size 2D, we have that the diameter of the intersection is at least 1, then there exists a large subfamily whose intersection has big diameter. So there exists an HF of size beta F, where beta is constant, such that the diameter of the intersection of H is at least C times the square root of T. So maybe not the whole intersection has a large diameter, but you could take a lot of the sets in F and achieve a big diameter intersection. And this is kind of a specialization here. So now I wanted to move any questions? Okay. So now I wanted to state the main results. So first, some notation. We let bracket n be the numbers 1 to n. And this notation P at most k of bracket n are the subsets of size at most k and n. And finally, if we have just some sets, we let k sub a, and a subset a and n, let k sub a be the intersection of the ki's for which I is in A. So the Helly-type theorem in 2021 we found was the following. Again, we start with a finite family of convex sets, and this time I spell them out, K1 to Kn, a finite family of convex sets in RD, such that the intersection of all the sets, which we denote by K, so K is K bracket N in this notation. Take all the intersect all the sets, such that this intersection is a convex body. convex and compact. Then there exists a subset A, size at most 2D, and n from 1 to n, such that the volume of K sub A, so we intersect the sets Ki for which I is an A, is at most CD to the 3D over 2. So use the volume of K. And the diameter of Ka is at most CD squared times the diameter. So this Ka will satisfy both the volume and the diameter statement. Any questions so far? So in particular, there's a small improvement of diameter, which is delta of D is now at most 2. So we're aiming for 1/2, but we have 2.
Can I ask a question?
Yes.
I'm confused about the difference between convex set and convex body.
Yeah, so convex sets, for example, a closed half space is unbounded, but convex bodies must be compact, so closed and bounded.
Okay. Thank you.
Thank you for asking.
Yeah, thank you. So this theorem, the approach we had, there's a crucial lemma, which I'll write down in a second. And it's going to seem a little bit unrelated to choosing convex sets, but I will motivate it afterwards. But kind of the big idea is that if we consider half spaces for the KIs, we can intersect them to get a polytope, which can be thought of as a finite intersection of half spaces, or alternatively, the convex hull of some amount of points in RD. And this lemma allows us to choose vertices, which by polarity will correspond to half spaces. So the lemma is the following. We let lambda be greater than 0, and Q in RD is a polytope. So it's a convex hull of a finite number of points, or intersection of a finite number of half spaces, such that Q sits inside minus lambda Q. This is scaling through the origin. And this statement here, an example of it is perhaps if we had a triangle as Q, and we have a origin in the interior, then minus D times Q would contain Q. Then there exist 2D vertices of Q whose convex hull Q prime satisfies another inclusion. So Q sits inside minus lambda plus 2 times D times Q prime. So to clarify, let me draw a small picture. Say this is Q, and let's just say this is the origin here. Then it says we can choose 2D vertices, so maybe the bottom 4, whose convex hull, which we call Q prime, satisfies minus some amount contains Q. So perhaps this would be minus lambda plus 2 times D times Q prime. And so if these KIs in our original theorem are closed half spaces, then we do indeed get a polytope. So that's kind of roughly where this lemma comes from. And it's actually in a strengthening of the diameter proof that Ivanov and Nasodi had most recently in 2021, where they showed exactly the following statement with the same hypotheses, except there is a factor of d squared here instead of d. So any questions about the statement so far? So I wanted to give some ideas behind what tools are used in this, in the proof of this lemma and the proof of the Helly-type theorem. So we'll start with the lemma, and then we'll see how the lemma ties in to the main theorem. So of lemma. So we start with a polytope Q. So maybe Q looks like this is Q. And the first thing we notice is that the origin must be inside the interior of Q. If it wasn't, the origin was somewhere here, then minus lambda Q would lie on the other side of Q. So we could take a separating hyperplane through the origin that would cut the two apart. However, we assumed that Q sits inside minus lambda Q. So implies that the origin is in the interior. So let's just say the origin is perhaps here. So the idea now is to choose 2D vertices of Q such that we can scale it appropriately to take Q. So we're going to choose D vertices now with the following method. So we consider the set of simplices with vertices 0, Q1, Q2, QD, such that QI is a vertex of Q. And we're going to take a simplex S in here, such that S has maximal volume. So, for example, in the plane, this would mean that we're going over all pairs of vertices in Q, and this is a finite number. And we're going to choose a simplex S such that it has maximal volume among all such simplices in this set. So maybe we choose these two vertices. So then S in this case would be the following triangle. And choosing this simplex actually tells us a lot about where Q must live. So to see that, let's name the vertices V1. Maybe this one's V1 and this one is VD. In D dimensions, we choose D vertices. So first of all, if we kind of extend this span and consider the hyperplane, it's called hyperplane H1, which is the span of the vertices of the simplex F, except VI. So in this case, so except V1. So in this case, this would just only be the span of V1 because we're looking at the span of V1, V2 minus V1. So we're just looking at this hyperplane. And we translate it up to pass through VD. This is H1 plus VD. And this down here, H1 minus VD. So the observation here is that any vertex of Q must lie in this strip. And the reason is because if there was a vertex of Q outside of the strip, then what we could do is we could take that vertex along with except VD, take out VD and replace Q with VD. So we get a simplex of larger volume because the projection of Q onto 0v1 is larger than the projection of VD onto 0v1. So that would be a contradiction to the fact that S is chosen with maximal volume. So this means all of the vertices in Q must lie in the strip, which is the strip such that the projection of VD onto this hyperplane is at all the points such that this projection is the maximal projection size. Any questions about this set? And we can repeat this again. So if we take this hyperplane through all the span by all the vertices but V1, and we look at how it passes through V1, then again, Q must lie inside that strip. So here's another color. Q lies inside the intersection of these two strips, which looks like a parallelogram in 2 dimensions, but in higher dimensions, it's a parallelotope. So, which is an affine image of a cube. So we can let P be the intersection of these strips. Maybe I call this strip L1, this strip L2, or LD in D dimensions. So this is what P is. And we just showed that Q sits inside all of these strips, so Q must lie inside P. So P is simpler to work with than Q. So we're actually going to scale our eventual choice of 2D vertices, their convex hull, to contain P. And the way we do this is actually, by scaling the simplex S appropriately. So we let S prime be the smallest homothetic copy. Oops. I realized I jumped logic, but we're here and then we moved over here. Okay. S prime be the smallest homothetic copy of S containing P. So in this case, S will be translated from the origin to this point here. And it will look something like this. Maybe I need another one. This is S prime. Okay. And this is P. And then we kind of do some coordinates. These are the main kind of objects we use. Then we do a little bit of coordinates to show that Q sits inside P. We derived that already. Sits inside S prime. And it turns out that the correct scaling factor for S prime is minus 2D times S plus some translate U. The 2D can be seen if we take S, assume is the standard basis vectors of RD. So now we have the simplex with vertices 0, E1, E2, all the way to ED. And we scale it by D. It turns out that that new simplex contains the unit Q 0, 1 to the D. So, and when we kind of translate over to this setting, it will contain this small parallelogram, and then we need to scale by 2. That kind of intuition where this 2D comes from. But we have this, and then this sits inside minus lambda plus 2 times d times q prime. So I didn't actually explain where all of the 2D vertices come from. I've only promised you that vertices d1 to bd are here. But the other d vertices will come from the other side of the simplex. It'll come from kind of choosing vertices on the opposite side of Q so that we could contain this simplex at the time. That's the intuition. Any questions about this? Okay, so I wanted to ask whether the audience is familiar with polarity in convex geometry or kind of. Okay, briefly, I will.
Yes. Good.
Yes.
Thank you. That's it for the video.
I will see a few words. So, a few words about polarity. So, we start with a convex set and RD. And the polar of K is another convex set. And we denote it by K polar. And formally, it's the set of points such that the inner product of that point with every point of K is at most 1. But without going too much into the details, there are some key examples. So if we have a half space that contains the origin and it's closed, say, and let's say the projection of the origin onto this half space supporting the hyperplane supporting this half space, let's say this distance is d, then the polar is a normal segment with length 1 over d. That's stemmed at the origin. And polars behave nicely under intersections. So let's say we have a ball, and we have five half spaces that each contain the ball. So their intersection is this pentagon here. Then if we take the polar of just, let's say, this left half space, so this is the unit ball. Then we get this unit normal segment. When we take the polar of this half space, we get this unit normal segment. Similarly, we get these. And since the projection of the origin onto this half space down hyperplane down here is larger than 1, that means the normal in this direction is less than 1. And it turns out that since K is the intersection of these 5 half spaces, the polar is the convex hull of the union of these 5 normal segments. So that's that. And one other fact we'll need is called John's theorem. 1948. It says that a convex body, so a convex compact set K in RD has a maximal volume ellipsoid inside it, E inside K. So Fritz John proved this, and it's now called the John ellipsoid. The John ellipsoid. Okay. And if E is the unit ball BD, so this is the unit ball, the set of all points of norm, Euclidean norm at most 1, then K is called in John's position. So John proved that if K is in John's position, so perhaps this ball here is the maximum volume ellipsoid of this pentagon. If that's the case, then if K is in John's position, then K sits inside minus d cap. And this is great for us because we get to use the lemma. And we'll see how it's applied in a second. But any questions about polarity or John's theorem? Okay, so now I will say a word about the proof of the main Helly-type theorem here. So proof of Helly-type theorem. I might need to draw a little more. Is it okay if I erase the polarity?
Sure.
So when Baran, Kachelski, and Pop started thinking about the statement, they proved in their original paper that it suffices to think about the KIs being closed half spaces. So any convex body, any convex compact set can be written as the intersection of certain closed half spaces, one at each point of the boundary. But there might be infinitely many. So they kind of had a topological argument saying that no, it actually suffices to consider finitely many convex sets, which are all just closed half spaces. So K, which we said was the intersection of all the convex sets, in this case is a dimensional polytope. Just because it's the intersection of a finite number of closed half spaces. So maybe we have perhaps this is what it looks like, and these half spaces all point inwards. So K is pentagon here. So the main claim in this is that instead of considering these two statements, we consider two statements that are invariant under affine transformations. So the statement is that there exists a subset A of size at most 2D from 1 to n, such that two statements hold. The volume statement, an inclusion statement first, Ka sits inside minus 2D squared K. So the intersection of the Ki is just an A can be contained in this homothetic factor of K. And the second statement is that the volume of Ka is at most CD with 3D over 2 times the volume of K. These are the two statements. And notice that if we kind of hit Ka and K with a matrix, both of these statements still hold. Inclusion still hold. Volume is behaves well under affine transformations. So it suffices. We said by John's theorem there existed unique maximal ellipsoid inside K. We may as well assume it's the unit ball just by taking an affine transformation of that ellipsoid to the unit ball. So assuming K in John's position. So in this case, so maybe the maximum volume ellipsoid is the unit ball This is the radius 1 ball. So now, as promised, we'll take the polar. So kind of already did that for this diagram or something very similar. So we have these unit normals. And this distance is greater than 1, so maybe this normal has distance less than 1. So, and then this is the polar figure we get. We'll call this Q. So Q is K polar.
And let me just quickly say that it's 7, but we're gonna give Matthew some more time because we started late. Sorry.
Right, and so the motivation is that we want to choose vertices of Q, which correspond to half spaces of K, just by polarity. The polar of a half space is this unit normal, and choosing vertices is nice with this lemma. But to apply this lemma, we need some sort of factor lambda such that Q sits inside minus lambda Q, and it's easy to see that Q sits inside minus dq. And well, K sits inside minus dk from John's theorem, because K is in John's position. And it turns out when you take the polar of an inclusion, the inclusion reverses. And the constant minus d times k becomes 1 over d times q. And just moving that d over to the other side, minus d to the other side, gets you this inclusion. So we can apply the lemma to find 2D vertices of Q, whose convex pole Q prime satisfies Q sits inside. Well, lambda is d in this case, so it's minus d plus 2 times d, or bounded above by 2 times d squared. Minus 2d squared times q. So we have this inclusion, and maybe q prime in this case is these 4 vertices. So this is q prime. And finally, the last step to this is that these vertices, they correspond to the half spaces. So Q prime polar is Ka for some A and of size at most 2D from one side. So the polar of this is the intersection of this half space, this half space, this half space, and this half space. This is Q prime polar or Ka. And when we take the polar of Q sits inside minus 2d squared Q prime, so taking the polar of this, we get K, the polar of Q is K, take the polar twice. The inclusion reverses, we get 1 over 2d squared times Ka. And this is exactly A. And I won't show B right now, but the main idea behind B is that we squeezed Q and Q prime in the lemma, proof of the lemma between a special parallelotope, which was centrally symmetric, because it was the intersection of these strips, which were symmetric about the origin. And we could use an inequality on volumes called the Blaschke-Santel inequality, which helps bound volumes of centrally symmetric convex bodies. So we can take advantage of that to prove B. And that's really the main idea of the proof. And just to say a word or two about further directions, it would be nice to prove such a statement only focusing on polytopes in John's position and improving the constant, because that's what we really use. when showing our proof, we move our intersection into a position such that the maximum volume ellipsoid is the unit ball. So it'd be nice to improve this constant, which becomes of order d squared when we're in John's position. And we can take advantage of some analytical properties of these special points because they're in a position called John's decomposition of the identity. So yeah, that's all I had planned for today. Thank you.
Like to hear real clapping again. Any questions?
Uh,
Yeah.